Hi, everyone. Welcome back. We are so excited to have you for our next panel. This next session is going to be a reverse pitch led by Adrian Kelly from EPRI. I'm going to pass it over to Adrian to please introduce his panel. Thank you, guys. Enjoy.
This session will be focused on the transmission and distribution grids, how we can make AI machine learning techniques useful to transmission and distribution system operators as we make the transition towards decarbonized, decentralized, and digitalized grid. I will be joined today by colleagues from PPL, Joel Eline, and from Terna in Italy by Leonardo Petrucci, who will speak on their unique company's perspectives on utilizing AI and machine learning in their grid operations. Each session will take roughly 10 or 15 minutes, and then we will happily take some questions in the Q&A field within the website application, which towards the end, if we have some time, we may put those questions to the speakers. I'd now like to hand over the first presentation, which is from PPL, and it's Joel Eline. Allow me to introduce Joel. He is the Director of Business Strategy and Data Analytics at PPL Electric Utilities. Joel is responsible for PPL's Data Science Centre of Excellence and leading PPL's digital transformation for asset management. His experience in managing maintenance and reliability engineering departments has helped form his perspective for delivering actionable data science products and business value. We look forward to your presentation. Any questions, please pop them in the Q&A, and we will speak after your slides. So over to you, Joel.
All right, thank you, Adrian. Good morning, everyone. Turn down my volume a little. Sorry about that. I was getting some feedback. So this morning, I'm going to present on PPL Electric Utilities' perspective on AI-assisted operators. And as a little bit of a backdrop to our strategy from an overall standpoint, we are in the process of going through a digital transformation at PPL. And one of our major focus areas is really around building a digital twin of our system. So it's a very asset management heavy focus around where our assets are, what the information coming back, what it tells us about their health and condition. At the same time, also is something else that we call smart delivery, which is how we're taking our operation centers to the next tier of technology and implementation and operating reliably and safely. The vision for the AI assisted operators is to really have not necessarily obviously like a general AI, but a little bit more narrow, certainly in terms of helping real-time decision making. So there's a lot of benefit to the timing and how fast an operator can respond to an emergent event, but also being able to identify and have preventative options to reduce risk. And some of those situations can be very simplistic, right? And that isn't necessarily where we're looking for the help. We're looking for the very complex, multi-input, that very fast and real time to help operators see and highlight what they couldn't see before and in a means that they couldn't have done before. I thought it was always important to talk about the data that we have available to go through this. So we have lots of information from the digital twin standpoint, a little bit more on the left side. We have a lot of data around our assets, where they're physically located, a lot of data about the information coming back. Some is extremely high fidelity, like waveform data. Some is very simplistic, just good old-fashioned nameplate, make, model, rating, type, lots of work history and what condition has changed to that asset over time. We also have a lot of environmental data that we use a lot too. And in dealing with something like an emergent or preventative type response, it's always important to know where your assets are located, what the weather condition is, or outage risk around it. Even some of the other variables, as something like vegetation outage risk, which might impact the electrical asset. In terms of a little bit more on the operational side of data, working in the bottom right-hand corner, we have deployed smart grid at PPL Electric Utilities. So we have a lot of the parts and pieces that come with that can help influence that data model. We have electrical connectivity, so how our assets are electrically related to each other. We also have physical orientation. We have load direction, system arrangement, not just where they are physically, but their status, whether they're normally open, normally closed. And we also know the location and outputs, or I should say more inputs, of DER and other generation assets on our grid. Like any other utility from an operations, looking at like the grid type metrics in the top right corner, we have the typical SCADA or electrical arrangement information: volts, amps, ohms. When we have a particular fault, we'll have fault magnitudes, and we certainly have much more technical information along the way. But what's immediately available is always fault magnitude. Distance and location is sometimes very important. And then also at the same time, we have to operate within certain parameters, and whether that's a voltage condition or line ratings and loading. So we can't necessarily just push power around. It has to fall within our criteria to operate our system safely. Trying to advance. Oh, sorry, jumped the gun. All right, so it's a pretty wide open world of an AI assisted operator, and trying to narrow that down into two specific capabilities that we're after. And one is really proactive or preventative actions to lessen the impact of an outage. So before an outage occurs, if we see a particular risk, being able to see the opportunity to move around power or reduce the impact of customers if we believe there's a high probability of something occurring, or if it does, what can we do about that immediately to see the option to restore the customers, partial and whole. But again, if we can do that quickly, we really reduce our permanent outages, and obviously the customer will still see a momentary, but we're gaining a little bit on the safety side as well. There's a lot of other options that you could also explore from expected outcomes. We could get into things like voltage control, although that wasn't necessarily around an emergent outage. Voltage could be part of an emergent outage. If we have AI helping our operators, we can certainly expect to see a lot of cost savings. And also when you're looking at off shifts, having somebody that doesn't necessarily have any kind of fatigue, and then you're not exposing yourself to any kind of human performance issues, there's a lot of benefits to having that machine help the human. I would say last but not least, we're certainly having an eye in the future around distributed energy resources and being able to understand them, not necessarily control them, I won't say that part, but be able to make sure our system is stable and reliable. And that is the end of PPL's AI assisted operators. Thank you. Turning it back over to you, Adrian.
Okay. Thank you very much. Thank you very much, Joel. Very much appreciated. A very interesting conversation on the future of operations from the distribution perspective. If we just want to remain online, if there's anybody that has any questions, remember, please pop them into the Q&A box, and we will take them or put them to Joel in real time or after the presentations are complete. Thank you for that. The next presentation is from myself and Antoine Marot. It was intended to be from Antoine, but he couldn't quite make it. But we do collaborate on a project, so it's I think okay for me to take the slides and to present on this topic. So just to give you a brief introduction of Antoine, in his absence, he is the lead scientist for AI at RTE. RTE are the transmission system operator of all of France. He has a double master's degree in engineering from the École College in Paris and Stanford University. He interned at Tesla Motors and joined the RTE R&D team on the Apogee project 6 years ago. with the long-term goal to develop a personal assistant for control room operators with AI. Through collaboration with INRINA, he supervised several PhD students on augmented power system simulators with AI and human intelligent machine interactions, with a strong focus on interoperability. In terms of myself, I am the principal project manager of situation awareness, transmission system operations, and the control center of the future within EPRI. My work focuses on improving workload and manageability for human operators, managing real-time bulk systems in terms of alarm management, human-machine interface design, situational awareness, training, and also interaction with digital assistants. Both Antoine from RTE and myself in EPRI collaborated on the project that we will talk about today, which is entitled Learning to Run a Power Network, or L2RPN. Today, I hope to give some context on the need for solutions such as L2RPN and the tool that Joel helpfully explained and the tool that Leonardo will explain in the presentation following this one. Let me just move the slide on. That should work. Not too far, of course. So to begin with, let's define what the system operations challenge is. Since this is a reverse pitch, it's helpful for us to explain, us as experts on the power system, to explain to those that may be unfamiliar with the challenges, what the main challenges are. We've helpfully broken these down into three, what's usually considered 3Ds, but I've expanded to a fourth D at the bottom. These are decarbonization at the top, which is the effect of adding more renewable, cleaner energy resources to power systems all over the world. Everybody should be familiar with this, the need to get more renewable, sustainable energy resources into our system. And this has had a major effect on the operations of bulk power systems across the world. The second element is decentralization. So where these new resources from decarbonized sources are being connected onto the system is disconnected from the load centers. For example, in the past, we used to be able to connect a large generator site in the middle of a city or on the outskirts of a city and pipe that power directly into the city, thus serving the needs of the demand within the city. Nowadays, with the move to decarbonized energy, these resources are located far from the load centers. So they may be on the coast, where there's wind, they may be in mountains where there's increased wind, or they may be in sunny regions to attract solar power. So this means that resources are decentralized from load, and we have to find smarter ways to connect or ship that power from the resources into the load centers. The third D is digitalization. So like most industries, power system operators, as explained by Joel, most utilities or system operators around the world are making moves, strong moves towards a digitalization of their data sources, of their documentation, of their system models. So this is happening quite rapidly. There's a multitude now of data available in house with utilities and operators, and the question becomes, how do we use that data in a more succinct way to drive and improve decision making. The fourth D, and if you notice, I was trying to shoehorn the D element in here, but I call this one demand disruption. So what we have here is a move towards what was regular, predictable use of energy from you and I as consumers to something that now becomes more variable. So we plug in electric car at different times of the day. Our smart devices turn on and off power dependent on what the market price is, which is dependent on other variables. So the predictability of our load patterns is changing and shifting, and demand is now becoming variable. These 4 Ds from the integrated grid are now feeding into cause issues with grid operations patterns. So you can see on the right, if generation switches location from traditional locations to other locations and demand starts to become variable, the mental models that operators use when sitting in the control centers have to shift. So the models that they use to manage the system for years and years are now quite different. And we, as in EPRI and the wider utility community, have to work to try to improve on those mental models and how they change. I explain these in a little bit more detail here on the slides. So let's focus on the challenges along the bottom. So what are the challenges that operators are facing, and how can AI, machine learning, reinforcement learning, the tools that you as vendors bring to the party, what tools do we need to solve with these 4Ds as the challenge? The first one is congestion. So congestion means much like traffic or traffic congestion or network congestion, we also have electricity congestion. So this is power from various locations trying to get to a source, and lines being overloaded, assets being overloaded, and issues with sort of lines disconnecting themselves because they're overloaded, or generation being used suboptimally to resolve congestion issues. So we feel this is a very good use case for AI, which I'll explain as part of the challenge. The next part is renewable spilling. What we mean by this is, while it would be optimal to use renewable energy all of the time, as you know, sun shines brightest at 12 p.m. The wind doesn't always blow. So how can we incorporate as much renewables as possible onto the system to meet load without disconnecting it or spilling it or not using it? So that is a huge challenge, trying to minimize the amount of constrained energy on the system. So can we develop ways to optimize this while meeting your congestion needs? Third element, stability. So grids are getting, shall we say, a little bit weaker as you disconnect a lot of large spinning masses and connect smaller inverter power electronic devices around the system. The grid will inherently become weaker, so there's stability challenges with how the system can stay together and react and respond to disturbances. Variability I spoke about, that's both generation variability and also demand variability. So, forecasting, can we get accurate renewable energy forecasts? Can we get accurate demand forecasts based on weather, smart device data, smart meter data? Can these improve? And lastly, contingencies. So congestion is not enough. You also have to manage the system that takes account of the loss of a large load or the loss of a large piece of equipment or line on the system. The system must be stable and congestion free, even for the loss of these large units. These are the first 5 challenges associated with, I guess, the first 2 Ds in the 4D paradigm. On the next slide, I have another 2 or another 5. This will advance. Data architecture is the first one we see there. We've talked about digitalization, but is there an architecture to enable quality, well-governed, clean data to flow around the network and get to the applications that's needed? Model validation. So we've got lots of good models of the system. Can we validate these in real time? Can we make sure that when an event happens, that these are validated so that the next event can be simulated properly? Forecasting, I spoke about. Electrification of society in general, that's transport, agriculture, heating, homes, trucking, aviation. Everything is moving in the direction of electrification thanks to the abundance of renewable resources. How can that be fitted into the electricity system operator needs? And then lastly, simulation. So can we create a good simulator model for the power system so that all of these things can be fed in and we can test various algorithms reasonably easily to see what works, what doesn't work when it comes to network operation? So these were the 4Ds. I hope you keep them in mind. These are the challenges that keep system operators right around the world up late at night, wondering if the system will stay stable and trying to prevent major blackouts in the system or major loss of load. Trying to advance. So the question becomes, and this is a slide from RTE that they like to use, is the paradigm of AI and electricity. So famous quote by Andrew Ng, who's the famous AI scientist, that AI is the new electricity. So if the 19th century or the 18th, 20th century was the century for electricity, grids is the 21st century, the century for AI. And then where's the nexus? Where do they meet? Where do they cross cut? And can we use AI, machine learning, and the boundary of the wealth of knowledge, experience, exceptionally good companies and expertise right across the world to solve the challenges that we as system operators will be facing as we move through the decades, trying to solve these 4D challenges. I wanted to speak here a little bit about what the use cases are for network operations, and I've got a lot of these. In general, what we find is that the use cases are there are a lot of use cases, and in general there is a lot of data within utilities that they like to that they have available, and we as in EPRI through the AI initiative are working with utilities to get that data into a safe and secure environment for EPRI researchers and other researchers to work with. This is just a patch quilt of a few that we came up with, but for those on the call that are wondering about what are good, where to apply, or are any of the areas of expertise useful, there is a multitude here of both use cases and a multitude of data. The question is trying to get this data safely secured, get people access to it, get people working on it. But there's use cases on natural language processing in system operations, how to encode experience from people to use speech to talk through what they see as challenges on the system. Demand forecasting using neural networks is very advanced and has been there for a few years, but that's advancing still further. Weather forecasting, obviously a key one for operations. Alarm data analytics or analytics from system data and asset health. And using machine learning on this granular system data is very useful. Model management, so how do we improve on, get single sources of data, make sure that that's validated, improved. Security or stability assessment is another one. So you're seeing here, we're not short of use cases, and in general, I do say it with a caveat, we're not really short on data either. We have a lot of it. The question we kind of need is a way or a method or a location or a standard framework for processing this data to allow users to allow experts and users to kind of interact with the data in as seamless a way as possible. The one I want to focus on is network operations. We think that the L2RPN challenge is a very good use case for it. So what exactly is L2RPN, or is reinforcement learning? How is that applied in this case? So you can see on this slide 4 GIFs. Hopefully you can see it properly. I'm getting some feedback on my audio is not great, so I'll try to speak a little bit slower and clearer. Hopefully don't cut out. We use reinforcement learning, or Google has used it for to play Atari or solutions like this, or Go to develop kind of games, or using reinforcement learning in the gaming environment. That kind of evolved to the GIF at the bottom left on learning to run, which was a challenge set at a machine learning conference where engineers or scientists were encouraged to participate, where they programmed a sort of agent to learn how to run, essentially to mimic the actions of a person as they run or stumble across building blocks on the ground. So this is really innovative, exceptional project, and that was the inspiration for the RTE project, Learning to Run a Power Network. The consideration here is, can we put the network, the system network, into an environment that people can interact with it, develop agents using reinforcement learning, similar to learning to run, to actually learn to run a power network. network. This goes back to Neil Wilhurst's talk at the beginning of today's day, as well as Joel's talk before on this concept of a digital assistant in the control center. Can we have and develop an agent that sits alongside the human operator, parses these 4D challenges that are happening to them, decentralization, decarbonization, and simulates those on the grid, and can suggest actions to the operator in real time. So the L2RPN challenge is about trying to use learning to run as an inspiration, and seeing, can we use that same technique for learning to run an actual system in real time. So what we see here is that the operation of a grid is actually a very good, it can be cast into a Markov model like you see here, pretty straightforwardly, in terms of an agent oversees the environment, which is the grid. They take action on the grid, which is to switch, open a line, or restructure the network by opening or closing different points on the network. And they can also change the balance in the network. So they can increase the generation, reduce the demand, in some areas, so that if something happens on the grid or the environment, an action gets taken, and that state then gets fed back to the agent, who takes another action, and on to try to solve the problem. So the key thing to learn here is that if you take a power grid as it is normally, it can be reasonably straightforwardly cast into a decision-making framework like this one, so that agents can be developed and trained to work through the problems on a network. And the want to show here is the combination of the inspiration from learning to run plus casting the network into the Markov framework, which we saw here. Moved to develop a competition or a challenge in 2019, which extended into 2020, and will extend further into 2021. We call it L2RPN, learning to run a power network. And again, one of the key things with AI, machine learning, is start small, figure that out, figure out the problem there, and try to scale the problem as you go. So what we have done is with this is start with a very small smart grid, 14 nodes, maybe 20 lines interconnected, and put it out to the wider world to see, can you get an agent to control this grid, to keep power flowing, prevent it from blacking out, and stop overloads on the network. This was very successful. We've got some really interesting results through 2019, which went to the launch of the competition in 2020. Which focused on two different kind of areas. So in 2020, we decided to scale the network up from 14 down to up to 114 different systems, and segregated different parts of it. So we ran a challenge in the early part of 2020, which again was successful. And we're all the time building participants from new countries, new universities, new expertise. And then in the summer of 2020, we launched a challenge for NeurIPS, the Sustainable World Challenge, and this was split into two different tracks. One which was focused on robustness. So by that we meant the agent had to control the grid, and while under attack from an adversarial agent. So that adversarial agent was disconnecting lines at random, and the agent was tasked with responding to those disconnections and adjusting the nodes on the grid or the generation on the grid. The second one was about adaptability. So here we had two different forms of a grid. So we had a test grid with conventional generation sources, and a second grid with generation sources from renewables. So this was to develop an agent that could be adaptable or workable in both a conventional grid, but also one that could work with very variable wind generation, solar generation at different nodes. And this was across a wider 114 bus grid. So competition entrants essentially were encouraged to write code to develop agents that could either be compete in either track or both. In some cases, to be able to control the grid under attack from an adversary, consider that to be a weather event or a disconnection for an overload, or else an agent that's adaptable to various different generation targets. This was extremely successful. We had around 500 participants from right across the world. We collaborated with here in EPRI with, well, it was a joint collaboration between RTE in France, ourselves in EPRI, Google, and University College London and IQT Labs, who set the sponsorship for the challenge. And the results were extremely innovative. In blind tests of the agents after these, the top agents were able to maintain the grid with grid scenarios they had never seen before. Were able to keep the grid alive and active in 16 out of 24 kind of blind scenarios that they had never seen before. So they were able to train on data sets that we gave them, but on blind tests they were able to keep the grid up and active in that number, which is exceptional result. This year, we really want to move to focus a little bit more now on trust and building the relationship between an operator sitting at a desk and what the agent's output is. So what we're going to do is to incentivize or reward agents that are developed that give a prediction on how good their decision is. So we don't want an agent to say, switch out this line, do it now. And then the operator does it, but without any kind of context on how good or bad that decision is. So in this year's competition, it's expected that the agents are designed to basically say, you should switch out this line. I'm 60% confident it'll cause a positive result with a 40% downside, and then it's up to the agent then to make that consideration to say, yeah, that's I'm willing to live with that, or that's a good decision, or not. So this is essential, right? Wherever we talk to utilities, and Neil mentioned it this morning as well, is that trust element, and we're not here to develop a thing to remove humans entirely from the loop. We need humans in there. Human operators in there, of course, with their experience. This is to help them as a kind of autopilot in the background. So the competition, which will be launched very soon in July, it's due to start. We have a website called epri.com/L2RPN. All of the details on what I've spoken on is there. There's videos, there's slides, there's papers. This is our repository for this type of work. It's all there. But I would encourage participants who haven't heard from this before, please engage. It's at a really, really early stage of research. So while we have some good results, it's very early, and we kind of wanted to foster a kind of collaborative community right across the world. So not just focus on particular country or area, try to work together across geographical boundaries, focus on kind of open sourcing of innovative solutions and tools. So the agents that won the competition last year have open sourced their code that's available for people to work on and iterate to. So really, we want to kind of foster a sort of space race type environment here. Keep setting challenges, keep incentivizing innovation, keep incentivizing collaboration, open sourcing, continue to talk about it, and link up utilities and operators with the wider machine learning community. And then just a summary on this, the 4Ds are kind of coming or are here. So remember them, and these are I spoke about the challenges that's presenting to us in EPRI and for system operators around the world, and our tools just might not be adequate. That's why we have to reach out to you guys as machine learning vendors and experts to try to help power system engineers who have continually worked with a set of tools, but now kind of need some help to break down some of these barriers. There's many use cases. We focused on one. We in EPRI can talk about any of these if you wanted, but we focused on one here on network operation. We think that you should grow a community, setting challenges, setting incentives, and then open sourcing. And then lastly, guess we think reinforcement learning has shown great potential so far through L2RPN for these types of digital assistant control center applications. So please feel free, join the community, email us, get on the website and get in touch on LinkedIn, and we're happy to discuss this in more detail to grow the collaborative. So if you've got any questions, you can just pop them into the chat box. We'll take them after the last presentation, which is, I'd like to pass over to the last presenter today, who is Leonardo, who's the system operator for Italy. So very similar to RTE, to give context, only in Italy. So Leonardo is an engineer at the innovation factory for the system operator for Terna. He graduated from the Politecnico di Torino in energy engineering, and he started working in 2018 in the innovation department of Terna, the Italian system operator. He mainly focuses on innovative projects regarding the topic of AI and machine learning. And the presentation today will illustrate the opportunity for TSOs to develop new tools and the safe management of the power system in the context of very steep increase in distributed energy resources. And the topics addressed are around forecasting of load and res generation, analysis of thermoelectric installed capacity unavailability for adequacy assessments, and improvement in DER observability. So hopefully this Leonardo's presentation will complement what I just spoke about and what Joel just spoke about. So the need to come up with a new toolkit for the challenges that we face in the future. So over to you, Leonardo.
Yes, thank you. Good morning to everybody. And as you said, I took quite the backward approach, and it's going to complement well with your presentation. And I'm going to speak about a very pragmatical use case we applied. And from there, I'm going to draw the conclusion and turn inside the implementation of machine learning technologies. So what's the problem? Here are some brief definition. As maybe many of you may be aware of, observability is basically the ability of TSOs to observe in real time every node of the high voltage line, and in order to guarantee safe operation in real time. And the state of the art for all TSO is that everything that is connected to the high voltage level, of course, is observable directly, but with a measurement. What's not so possible to see in real time is everything that is on the DSO side, so medium and low voltage level, because of course that's not our grid, and we do not have any assets on that. But in these years, the impact of distributed energy resources become so big that also TSOs need to observe what's on there. And here we introduce the concept of indirect observability, which is the capability to observe somehow these many points, but without all those measurements, because as you can see from the next slides, yes, the amount of points on the medium low voltage level is so much higher, and we're talking about 880,000 points of measurements, which is 99% of the generation units in Italy, and that's not feasible to measure them all with installing a device. Thankfully, that amount just to 25% of the installed capacity overall. But as we can see on the left-hand side of this slide, the amount of non-programmable renewable sources is going to increase more and more. We expect now 70 gigawatts by 2030, according to our latest government statings. And let's say 1/3 of that is going to be on the DSO side. So we need to do something about that, because as you can see in the next slide, which is going to take some time, sorry. We need to integrate this observability for grid calculation, for the OPF, for the evaluation of inertia, the evaluation of correct use of the fence plants, and so on. And so that we needed to do something about it. For now, we have gone with what is highlighted as scenario 1, So we wanted a tool that could estimate in real time with a 15-minute run frequency all the generation and load aggregated by transformer of substation level, so at the node between high voltage and low voltage and medium voltage, sorry. And what we did was we identify a technological concept, which is the following. We wanted to exploit machine learning models to estimate the most possible amount of generation by providing the ground truth, which is the power plant historical series and their characteristics, correlate them with weather data, which is the main driver for renewables, of course, and where possible to include some sample measurements to help the network estimate the nearby plants. And this quick slide just to say that this was not an ordinary project, also for the procurement side, and this is going to be, sorry, the slide went, okay. And so usually for regulated subjects such as us, if we want to buy something, we make a standard tender because we are under some public laws, and we specify it to the minimum detail and we buy it. But with machine learning, this is not the case because most of the time the solution has to be heavily customized. And as you can see, we went for another approach, which is the pre-commercial tender, in which we experimented with 4 different partners, and we developed some POC, then we developed the online pilot, and we increased our know-how and we understood what was the best solution. So let's talk about the most important stuff now. So machine learning means data. And as you understood, the problem was to estimate the distributed generation. So of course the data required are the characteristic of the production units. So what type, if it's solar, wind, thermoelectric, where is it, so I can correlate it with weather data. What's the rated power for physical constraints? And the challenge with this data is that we do not know, we do not have many technical info such as the tilt and azimuth angle of panels. So this is an input that was missing for our model. And the same goes for the substation of the distributor. We need to know where they are, how many transformers. We have 2,000 substation with 2 or 3 transformers, so about 4,000 transformers. And one critical challenge here was that we did not have at first the correlation between generation unit and the distribution substation, which was a problem because we wanted the aggregation level, but we asked that to the DSO, and this is going to be a very relevant part in this project. And going on with the data, weather data, I'm not going to spend too much time on this. We had a 4x4 kilometers grid. The only challenge here is that since it's a regular grid, we do not have data on point for the wind farms. So as you may well know, the forecasting of wind farms needs to have data on the wind turbine, which was not the case because we are talking about more than 4,000 power plants. And then let's talk about our ground truth, which is so-called metering historical series, which are the data that the DSO usually 1 month delay to Terna, and these are the inflow energy measurement. So that's first problem is we want to estimate pure generation, pure load, and here we have inflow energy, so no self-consumption details. And as I always say to my colleagues, no matter how good you are studying poetry, you will never learn to do math with that. So our networks needs the generation, not the inflow energy, and that's why we asked to the DSO for the generation historical measurements. With the problem that we couldn't have that many because this process is not so well implemented at the moment. So we had about 30K generation units historical series, over 80,000 power plants. So we had to do something about that too. Thankfully, we will see that machine learning can solve this problem. And of course, the telemetry, so the measurement of active and reactive power for the substation, because we need to ensure that in real time, the sum of all the generation aggregated and the load behind the substation equals to the telemetry we see. One last comment is that on the right hand side of this table, You can see the number of records. I didn't put the terabytes because everything is compressed, of course, but just to give you a key message that when dealing with machine learning problems for the power system, we are always dealing with big data problems, and this has an impact on infrastructure we will see later. Let's go to the next slide. I'm going to be very quick just to say that we operated within the system operation guidelines. So as mentioned, we asked for the installment of some sample plant measurements. We did within this regulatory frame, and our proposal agreed with the regulator was that we would acquire all the power plants measurement from the standard perimeter, which is everything that is with rated power more than 1 megawatts, which is about let's say 50% of the installed capacity in medium voltage level. And then we had to provide an insights on how many sample plant we should measure in the extended perimeter. And for this is a very nice thing. The next slide, it's an application to understand even before installing the measuring units, how to assess which are the most representative sample plants to measure so that we can estimate all the other bulk. And we did that with unsupervised machine learning. So we did only on medium voltage level because the data were clean only for that. And we distinguish between estimable sources and not estimable. So the wind and solar, of course, can be estimated by models. The thermoelectric and hydroelectric at that level with that many plants, since they are heavily influenced on the human control, it was not possible with the data available to estimate them with machine learning methods. So we just applied a simplified method, which means we simply took the one with the highest capacity, the installed capacity. So we identified about 7K plants that were our first guess to go on to give to the algorithm in backtest to see the feedback. And how did we do that? We did that with the following scheme. So we encoded the characteristic of the power plants into so the characteristic for the size, the location, the typology, and also the historical series, which is a very large number of records, as you may have seen from the previous table. We encoded that with some neural network in just 2 scalars. So we defined a vector, a coded vector for each units, and then this is called self-organizing maps. So we identified the clusters of these power plants. So we computed this mutually observability index, which is a function of the Euclidean distance on this bidimensional plane, to see which is the power plant that most represents the others. And that's how we got to that number. We built an optimization function that was function of these indexes, and we identified the most representative one. All the rest has to be estimated. And this is done with the supervised machine learning, which is what I'm going to explain from now on, and maybe the most interesting part. As I was mentioning before, the ground truth had some problem. So we had 3 types, maybe 4 types of historical series, as you can see here. Pure generation, in which the metering, so the inflow was exactly equal to the pure generation, because this is typical for wind farms or very big solar plants. This is not the case for smaller solar plants, and as you can see, we have the self-consumption family, in which the production is equal to the inflow only on the weekends, on the holidays. And then we have another type of historical series, which is the energy plant, which is a square waveform, which is integral, is equal to the production, but there is no such a profile in reality. How did we identify these 3 types of curves? We developed advanced white box models, so no machine learning involved, and we feed that to the characteristic we had of those plants, and we see when the curves produced by the white box models would match the one from the historical series. And the results you can see on the right. We reconstructed about less than 20% of the total power plants. But this was enough to train the neural networks. And this is finally the scheme of the estimation engine. As you can see, there is an offline procedure in which the white box models do just what I explained. So they reconstruct the ground truth, and there is the training of the neural networks. Then when the tool is online, there is the estimation by plants. So for all of those points we have seen before, the estimation of the generation and of the transformer power flow, so that we can compute by difference the load. And finally, we give from the DSO generation Kalman filter to optimize the generation and load so that we match the power telemetry at substation level. And this is done because the neural networks are not convoluted, so they are all independent estimates, but of course we know there is the solution must be the one that reconstruct the power exchange. Of course, there are several solutions. The Kalman filters, which thinks it's the best. And by adding some energy constraints, of course, you can do even better. So finally, some results to see if all this was worthy. And apparently it was, at least from the backtest. The tool now is going online. We are installing it in an environment which can produce input to the control room, but it's not integrated with the control room system. Of course, it's a prototype. And you can see for the PV generation and the wind generation, the results were quite good, especially for PV, of course, because it's easier. On the 3 scenarios, so in those 3 months, the normalized mean absolute error and the mean absolute error were always below the 10% requested from our dispatching control direction, and very few kilowatts, tens of kilowatts. And for wind, it was a bit for what I said. So the problem was that the wind measurement and prediction were not on the wind turbine, but all in all, even if the percentage error seems higher, if you see at the megawatts, it's really negligible for TSO operation. So it's still a good results. I want to change completely the point of view of the project and talk about the software architecture, so the infrastructure. This is very simplified infrastructure. As you can see from left to right, we have the databases. There is a series of layers which are Dockerized, from the extraction, transfer, and load mechanism up to the application layer where there are the models, and then finally the HMI. Why do I want to bring this up? Because many technologies that were proposed by the providers we work with, I listed some of these in these slides, especially for the DB and the Dockerization, were not in the Terna's blueprint for operational systems, because we never used them before, of course. And without that, we do not have maintenance licenses on those, and we cannot implement them in our operational centers. So I'm going to close back with the key learning, the first, which is just connected to what I just said, which is corporates must contemplate the adoption of additional hardware and software technologies for the use of these algorithms from an operational point of view. So not just for POC or prototypes, but for full integration in our systems. Then second key learning from the project and for developing a strategy to integrate this technology is that the regulated utilities, this is true just for the companies such as Terna, of course, need to use innovative procurement tools, since there is no ready-to-market or on-the-shelf solution. When dealing with the machine learning, customization is always needed, and this must be known to everybody. And finally, maybe the most important one, as you have seen, for the achievement of this project, what was the sharing of data and between stakeholders, especially from DSOs and producers. And there is a general need for utilities to share data more and more, and data and measurements. And with a data lake approach, probably this is food for thought, of course. But this is because machine learning needs adequate and sufficient data, which, as we have seen for distributed energy resources, is the most challenging part. So with that being said, I finished this presentation maybe even earlier than expected. And of course, if you have questions, I'd be happy to answer them.
Thank you very much, Leonardo. Thank you to Eric. Very good whistle-stop tour through that presentation. We do have a couple, and I know we've got a couple of minutes left, a couple of questions here. So I might ask Joel so somebody has asked, what is the extent of historical data sets available for outage prediction in PBL?
Sure. So I'll answer that. Maybe I'll start with the actual outage itself, and I'll work around a little bit in terms of the data ecosystem. Each of the outages that we have throughout history, and the data gets better as we go along, depending what systems are deployed. But at the very least, we have time of on a specific outage, but usually the location is down to the isolating device at the time of the outage. So it might not be the actual physical location of it, but what device operated, customers downstream, also cause code. What was it? A specific equipment failure? Was it vegetation? Live on wire? Those kinds of things. As we get more near term in terms of our outage data, we have actual fault location. So distance to fault is what we call it. But we get beyond that isolating device into like it's usually in this area. Again, might not be on the very specific granular asset level, but still the same type of information: time, restoration, number of customers, total minutes, those kinds of things. In terms of the other historical data that typically, or at least we've used before in previous outage prediction models, it's always what's changing in the world around it. So we have a lot of historical asset and maintenance. I'll term it maintenance information. So what have we done to the assets from a preventative maintenance, from a corrective maintenance throughout time? When's the last time we inspected that? Also in terms of our vegetation program, which for us plays in a lot into our outages as well. When was the last time we maintained this circuit in terms of clearing, what was removed, total trees removed versus side trim? There's a lot of other accessory information around it. The one piece that we don't have, and sometimes it's good to call out not what you have, but what you don't. We don't have historical system configuration. So at the time of that outage, what our system looked like, we don't necessarily retain. Now, in the past, we do know that doesn't change a whole lot over time. But again, we only have the current state as of today reflected in our system topography.
Interesting. Thanks, Joel. Leonardo, I might put the same question to you. What's the extent of your archive, and what data do you store?
Yeah, sure. I went a little faster on that part on the data. There is also the slide if we can take it back, but I can read it for you. So for weather data, of course, we had a very deep history. We have over 10 years because that's the SST we have always measured and providers always done. For the energy and power generations, we had only 3 years of historical depthness, which is enough. Usually, when you have 2 years or more, you are already good to go. And for the same went for the telemetry, so for the measurement from the SCADA for the transformer, about 3 years history.
Hi guys, thank you so much. All right, it looks like we are ready for a break. So we're gonna break here and we will be back at 12 p.m. noon. Thank you guys, we'll see you soon.